Assalamualaikum. Today our group would like to present about the geometric extremas in complex plane. This is our group teammates. First we have Iman Haikal as the GeoGebra architect. Second we have Afiq as the optimization specialist. Third we have Awang as the algebraic lead for circle and ellipse. Then lastly we have Irel as the technical editor and coordinator.
We begin by defining our complex number z as x plus yi. For this example, we have chosen a specific locus where z minus z0 is equal to 4, and we assign z0 the value of 2 plus 3i. By substituting this into the modulus formula and squaring both sides, we arrive at the Cartesian equations, and this describes a circle. The center coordinate for this circle is 2, 3 with a radius of 4. Now, let's find the modulus extrema. To find the maximum and minimum values of z, we look for the points on the circle closest to and furthest from the origin. Geometrically, these points lie on a line passing through the origin and the center. We calculated the gradient m as 3 over 2 by substituting y equals to 3 over 2 into our circle equation. We solve for the intersection points. This is the part where we solve for the quadratic form modulus. After expanding the equation, we get a quadratic 13x squared minus 52x minus 12 equal to 0. Using the quadratic formula, we find the x and y coordinates for the extrema. We also noted a general proof. The closest point z minimum is the center vector minus the unit vector of the center times the radius. This confirms our algebraic work. Next, we find the argument extrema. This occurs when a line from the origin is tangent to the circle. We substitute y equals to mx into the circle equation and set the discriminants to 0 because a tangent only touches the circle at one point. However, notice our result, 12m squared plus 12m plus 7 is equal to 0, has no real roots. So why were there no real roots for the tangents? We check the distance from the origin to the center, z0, which is 13 or about 3.6. Since the radius is 4, the origin lies inside the circle. This means the locus surrounds the origin and the arguments can take any value from negative pi to pi. Finally, we verify the tangent slopes using implicit differentiation. By differentiating the Cartesian form, we find the slope of the curve at any point. This confirms that the tangent slope is negative reciprocal of the radius slopes, providing a bridge between complex numbers, geometry, and calculus.
To find the locus of the complex point z defined by modulus z plus 2 plus modulus z minus 2 equals to 6, we first substitute z equals to x plus iy and perform a Cartesian conversion, squaring both sides twice to eliminate the radicals and arrive at the standard ellipse equation x squared over 9 plus y squared over 5 equals to 1. This reveals a center at 0, 0 with a semi-major axis a equals to 3 and semi-minor axis b equals to 5, which directly identifies the modulus extrema, a maximum value of z max equals to 3 at z equals to plus minus 3 and a minimum value of z minimum equals to 5 and plus minus I 5. As a result, we further confirm using optimization by differentiating the distance squared by substituting the line y equals to mx into the ellipse and applying the condition for a single point of contact. We determine the argument extrema to be slopes of m equals to plus minus 5 over 3. Finally, applying implicit differentiation to the ellipse equation yields the gradient function dy over dx equals to negative 5x over 9y, providing a complete mathematical reconstruction of elliptical locus from its complex definition to its geometric and calculus-based properties.
Hi, as you can see here, this is the GeoGebra illustration of the circular locus. First equation, x minus 2 squared plus y minus 3 squared equals to 16. This circle is centered at 2, 3 units with 4 units of radius. Second, y equals to 3 over 2x. This is the equation of the line that goes through all the circles. Next, x squared plus y squared equals to square root of 13 minus 4 squared. This is the smallest circle that you can barely see centered at the origin. Next, x squared plus y squared equals to square root of 13 plus 4 squared. Well, this is the biggest circle centered at the origin. And that's all for the GeoGebra illustration for the circular locus. Next up, GeoGebra illustration of the elliptical locus. First equation, x squared plus y squared equals to 9. So this is the equation of the red circle, the biggest red circle that you can see there, centered on the origin. Next, x squared minus x squared over 9 plus y squared over 5 equals to 1. So this is the equation of the ellipse in the orange color. And then x squared plus y squared equals to 5. This is the equation of the smallest circle centered at the origin. Next, y equals to negative square root of 5 over 3x. This is the equation of the red line, which has the negative slope. And finally, the positive of it, which is y equals to square root of 5 over 3x, the positive slope of line. So this is the GeoGebra illustration of the elliptical locus.
That's all from us. Thank you.